In this lecture, I'll talk about statistics and introduce some important terms. We'll learn about what is meant by statistics, what are the different branches of this field, and we'll get introduced to some important terms like variable, observation, data, and so on. So let's talk a little bit about statistics. So this is Education 510, which is an introductory course in statistics. What is really meant by this term? So if depending on the textbook that you're using, there are many different definitions of statistics. For example, statistics might be defined as the discipline or the science that concerns itself with collecting data, organizing data, summarizing data. You might see additional terms like interpreting data, analyzing data, and so on. What is common across all of these definitions is that statistics has something to do with data. I personally like a very simple definition of statistics, which states that statistics is the science of data. So I like this because it's a very concise definition, and it has two very important concepts. One is science and the other one is data. Let's go over each one of these. So statistics is the science of data. It's science in the sense that it consists of very rigid, inflexible rules. So when you're performing a statistical operation, you have to follow those rules, and you typically do not have a lot of flexibility. We want objectivity in this discipline. So if we have 100 people, for example, who are doing the same thing, who are running the same statistical procedure using the same data, then we want everybody to come up with the same answer. Just like mathematics, when you're solving a problem, there has to be a single correct answer. In statistics, we sometimes do not have a single correct answer, but everybody who is working with the same data will more or less come up with the same conclusion. So in this respect, it's science. There is a broader aspect to this, and I'll talk about this in a few minutes when we talk about hypothesis testing. This word science, is actually a reference to the scientific method. So I'll explain that in a minute. The second key term in this definition is data. And I want you to think about a very specific format whenever you see or hear the word data in this classroom. Now, the term data itself has many different meanings. So if you look up this term in a dictionary, most dictionaries will call it information or knowledge or something similar. There will be some sort of a synonymous term for this word. I want you to think about data in a very specific way. Each time you see or hear the word data, try to imagine a flat table that consists of rows and columns. So a grid-like pattern that has many different rows and many different columns. So here I have drawn a table that has a total of 4 rows and 3 columns. You should visualize this kind of a table. Something like this should come to your mind whenever you see or hear the word data in this class. This is a very specific format which is called a flat data table. There can be more complex, there are in fact more complex data structures. A flat data table is the simplest of data structures. And the good news is that it's one of the default formats that is used in most computer software programs. So this is the default, for example, in Excel. This is the default format in SPSS, SAS, Minitab. These are different computer programs that you can use for statistical analysis. So the table that I just used, it's a flat data file. A flat data table, and it consists of a grid-like pattern. It has a number of columns and a number of rows. In my example, the table has 3 columns and 4 rows. Each row in this grid-like pattern is called an observation. So row number 1 in this table, I'm going to call that observation number 1. Row number 2 is my observation number 2. Row number 3 represents observation number 3, and row number 4 is observation number 4. So each row is called an observation. This concept has other names. Sometimes it's called an instance or a record, or sometimes it's called an example, case, person, respondent, patient, depending on your context. We are going to call rows observations in this course. I sometimes might use other words like cases, but most of the time I will use the word observation to refer to rows in a table, in a flat data table. Each column in this format is called a variable. So I see there are 3 variables in this table. I'm going to call each one of these a variable. The leftmost column is thus our variable 1, and then the column next to that is variable 2, and the third column I'm going to call this variable 3. So we have a collection of rows and columns, or in other words, we have a collection of variables and observations. This collection of variables and values on those variables or observations is called data, or at least this is the specific sense in which we'll use this term in our class. Now, let me use some examples, some very simple examples of data sets that you might be familiar with. First of all, we need to understand that the group of observations that we are looking at, they represent something of interest to us, some element that is of interest to us. So, for example, if I'm interested in looking at a group of individuals, a group of human beings, then my observations are human beings. Each observation is an individual person or human being, and that person will occupy an independent row, a unique row in this table. So for instance, if I'm looking at a group of individuals, then there are 4 rows in this table, which means I have data from 4 individual persons. Data for person number 1 goes in row number 1, person 2's data goes in row number 2, everything related to person number 3, all information we have on person number 3, it goes in row number 3, and so on. In this case, we say that our unit of analysis is an individual person. This is an important term. A unit of analysis is actually an element of interest to us in a data set. If I'm looking at a group of cats, then my unit of analysis would be a cat. If I'm interested in examining a group of cars, then my unit of analysis would be an individual car. If I'm looking at a group of buildings, my unit of analysis would be an individual building, and so on. So let's take a look at some examples of variables where our unit of analysis is a person. So I'm going to create a new table here. This table also has several rows and several columns. Each column is a variable and each row is called an observation. The one thing specific about this table is that our unit of analysis is a person, which means I'm looking at a group of individuals. So each row represents an individual person. So my observation number 1 is actually person number 1. Observation number 2 is person number 2, and so on and so forth. I'm going to take a shortcut here rather than write the word person over and over again. So we have 5 individual persons here, and they are represented, each person is represented by a unique row in this table. We also have 3 columns here. These columns are variables. Now, before I go further, let me explain what a variable is. A variable is any characteristic or attribute or feature that varies across individuals in a group. We're not specifically talking about groups of human beings. When I use the word individual, it could be a group of individual cars, or a group of individual buildings, or trees, or cats, or some other thing of interest. It could be a living thing, it could be a non-living thing, it could be something abstract. For example, I could be interested in looking or examining a group of, examining a group of political theories, a completely abstract concept. I cannot touch a political theory, I cannot see it, but I can understand it, I can read about it, and so on. So it's an abstract concept. So our unit of analysis in that case, if I were examining a group of theories, would be an individual theory. So each individual theory would be represented in an independent row of this table. So back to this concept of a variable. What is a variable? A variable, again, is any characteristic, attribute, or feature that varies across individuals in a group. Let's, for simplicity, think about a group of individuals who are human beings, a group of persons. So what are the different features that people have? Right? Let's try to imagine a group of students. What different types of characteristics or features do students have? I can think of some. Each student, for example, has an age, a characteristic called age. In fact, you don't have to be a student in order to have age. Every person, every human being has this characteristic called age, depending on the year that you were born in. Each person has a characteristic called height, right? So you can identify with that. You're a person and you have a specific height, you're 6 feet tall or 5 feet tall or 5 feet 4 inches tall and so on. That is a characteristic or attribute that you have. Another example is weight and so on and so forth. I'm using a very specific term for all of these attributes. I'm using the word variable. And the reason I'm using this term is because if you look at a group of individuals and think about these different concepts, the values of these concepts will vary across these individuals in that group. So for example, if I have, say, 40 students in my classroom and I ask all of those 40 students the same question, what is your age? I'm going to get a variety of answers. Some students will tell me, assuming this is an undergraduate university level class, first year or second year class, some students will tell me they're 18 years old or 19 years old. Some students will tell me they're 22 years old. I will see this variation in age across students. The main thing is that I have this same concept age that is applicable to all 40 individuals in my classroom, all 40 students in my classroom, but I get different values from each individual person. It's okay if some of the values repeat themselves. So I could have multiple students in my classroom, for example, who are 20 years old. That's fine. But as long as I see any variation in this particular concept, in this particular feature across individuals in my group, I would call this a variable. So again, a variable is any feature or characteristic or attribute that varies across individuals in a group. So in a group of people, height is a variable, weight is a variable, age is a variable. In a group of students, GPA is a variable, or the percentage score on an exam is a variable, or the number of hours of study per week for all these students is a variable. It's extremely unlikely that everybody in a classroom, let's say a classroom of 40 students, studies the same number of hours every week. There will be variation in the number of hours. Somebody studies 10 hours during the week, another student studies 20 hours during the week, somebody else studied 15 hours during the week. There is a student maybe who did not study 0 hours during the week and so on. So we expect this kind of variation. Now let's assume that there is no variation for a particular concept. Everybody has the same value on that concept in a particular group. So for example, let's say I'm teaching a group of students and all of these are male students. The gender in this particular group is a constant. It's not a variable. Gender in this group is a characteristic that does not change when I go from student number 1 to student number 2 all the way to the last student in the classroom. When I ask everybody in this classroom, what's your gender? I basically get the same answer. Everybody responds male. Person number 1, what's your gender? Male. Person number 2, what's your gender? Male. Everybody in this classroom gives me the same answer. I don't see any variation at all in the answers. Therefore, this is not an example of a variable. In fact, this is an example of a constant. So conceptually, you can think of a constant as the opposite of a variable. Any feature that does not vary across individuals in a group, that is called a variable. So I'm going to use some hypothetical values in my table to demonstrate these three variables that I've listed here. I'll maybe add a few more to this list. So I'll start with age here, which is my variable number 1. This is my column number 1. Remember from our previous discussion up there in our first table that each column in this flat data table is called a variable. Each row is called an observation. Since my unit of analysis is a person, since I'm looking at a group of persons, a group of human beings, each row in my table is now called a person. It represents a person. Each observation is a person. And each column, each variable represents a feature of these persons. So the group of individuals that I'm looking at, one feature or characteristic they have is age. And I'm going to assume here that this is a variable, that when I ask all 5 individuals in my table, what is your age, I get different answers. So for example, the 5 individuals in the table give me these answers. Let's assume these are students. So, and these are undergraduate students. So person number 1, I ask this person, what is your age, rounded to the nearest year. And this person tells me my age is 20 years. I record 20 as the age of this person. Person number 2 tells me that she is 19 years old. Person number 3 tells me he is 18 years old. Person number 4 is 21 years old. And person number 5 also happens to be 20 years old. So here I have a small data set that consists of 5 observations. And I have basically information on age of 5 individuals in this data set. Now notice that if you look at column age, the values in this column are not the same. Right, so for some individuals the value is 20, another individual the value is 19. For person number 3 the value in this column is 18. As long as I see any variation in this column, as long as any two numbers or values in this column are different from each other, this column is called a variable. So age in this example is a variable. In fact, it's a very specific kind of variable. It's called a quantitative variable, and a very special kind of quantitative variable at that is called the ratio variable. But we'll talk about that in more detail in a different segment where we cover the scales of measurement. Right now, it is sufficient to understand that I have more than one value in this column. Therefore, this column represents a variable. Another example of a variable, let's pick the second item in our list, height. So I ask all of these students a second question. I ask each person, what's your height? And I get information from each person. We'll assume that everybody cooperates and everybody answers our question. In real life, when you ask somebody a question, they might not cooperate, particularly for some sensitive questions. If you ask somebody, how much money do you make? That person might not be comfortable giving you an answer. This is considered private information in many cultures. If you ask somebody how old they are, that person might not be comfortable giving that information. So what happens in real life is that sometimes the cells in a particular column representing a particular variable, values representing a particular variable, they're empty because a person did not provide that particular information. For simplicity, in this course, we are going to assume that everybody cooperates. We ask a group of 10 individuals several questions, and everybody cooperates, everybody answers those questions. This is just a simplifying assumption. Otherwise, we'll have a problem called missing values in our data set, which is a kind of a sub area of statistics, an area that is very close to my own heart because I wrote my doctoral dissertation in this area. So there are many different methods that you can use to deal with missing values. We're going to stay away from this topic for now, because it's sort of advanced for our course, and it's just going to make some things difficult for us. So we'll keep things relatively simple. We'll keep the concept simple for us and assume that whenever we gather information, we have no missing values. Everybody cooperates. Or another way of thinking about this is that if somebody does not give us full information, we just drop that person from our data set. We just don't include that person in any of the rows of our data set. So height in this table is another example of a variable. We're going to assume that we get different values on height when we ask these five individual persons how tall they are. So person number 1 tells us that he's 6 feet tall, 6 feet and 0 inches tall. Person number 2 is 5 feet and 6 inches tall. Person number 3 tells us that his height is 5 feet and 4 inches. Then we have somebody who's 5 feet and 9 inches tall, and then another person who's 5 feet and 3 inches tall. So again, I see variation in this column. So height is an example of a variable. If I had the same value throughout the column, then height would be a constant. It would not be a variable. Right now, height is a variable because I see a variety of information, a variety of different values in this column. Let's skip weight. Let's introduce a different kind of a variable. So for age and height, we have very special kinds of variables where we have numbers in both columns. Now let's think of a different attribute that cannot be represented by numbers. One example I can think of right now is the smoking status of an individual. So let's say we ask these 5 students the same question, which measures their smoking status. We ask each person a simple question: do you smoke? And there are 2 possible answers to that, yes or no. Right? So anyone who says yes we're going to classify that person as a smoker, and I'm going to represent smoker with an S. And anyone who says no, we're going to call that person a non-smoker. I'll represent non-smokers with an NS. All right, so we ask these 5 individual persons, what's your smoking status? And let's assume that we get a variety of answers. Remember, if we do not get a variety of answers in a column, then we're not really dealing with a variable. And in statistics, we're typically not very interested in constants. We're usually interested in examining and understanding the behavior of variables. So the third column in my data set, let's call this column smoking status. So we ask each person in this data set, do you smoke? And person number 1, and they all give us an answer. Person number 1 tells us, yes, I smoke. So we we classify person number 1 as a smoker. So I'm using S for smoker here. This person said yes to our question. Person number 2 and 3 both said no, so they are non-smokers. Person number 4 also said yes, so this person is a smoker. And person number 5 said no, so this person is also non-smoker. So out of 5 students, we have 3 smokers and 2 students who are non-smokers. I'm sorry, we have two students who are smokers and 3 students who are non-smokers. So is smoking status a variable? Does this third column represent a variable? The answer is yes, because if I look into this column, I can see that the values are not the same. I see different values. There are only 2 different values, non-smoker and smoker. Some of the values repeat themselves. The term smoker repeats itself twice for the first and the fourth person, and non-smoker repeats itself 3 times. That's absolutely fine. As long as any 2 values are different in this column represents a variable. So we have 3 examples of variables in this small data set, in this simple illustration. These are age, height, and smoking status. Now keep in mind that your data set, I've been saying that you have a bunch of observations from a group. I haven't actually explained what kind of group we are talking about, where this data actually comes from. There are 2 primary sources of data. The data either comes from a population or it comes from a sample. Let's talk about these a little bit. What is the difference between a population and a sample? Population versus sample. A population is a large group of individuals that we are interested in. Again, this does not have to be a group of human beings. It does not have to be a group of students or persons. It can be a group of anything that we're interested in, a group of textbooks, a group of computers, a group of cars, a group of buildings, a group of political theories, as I illustrated earlier, anything that we are interested in. So this group of things that we're interested in, it's called a population. For simplicity, right now, let's assume that this population is actually a group of human beings that we are interested in. A sample is a subset of the population. So a population represents a large group of individuals, and a sample is a part of that population. It's a subset of the population. Now, we typically assume that when a sample is selected from the population, it has the same features that the population has, but we'll talk about that in more detail when we get to 520. Right now, it is sufficient to assume that we're either talking about the large group of individuals that we're interested in, or we are talking about a small subset. Now, the question is, why would we ever be interested in a subset of that population? If my population of interest, the large group of individuals that I want to learn about, consists of 100 individuals, I'll use uppercase N here for population size, then why not just get the data from those 100 individuals? Why would we want to ever look at a small subset of this population? And the answer to that question is that sometimes, in fact, in most scenarios, in most practical situations, we typically do not have access to the entire population. In fact, in some cases, we don't even know what the entire population looks like. So we have no idea, for instance, what the population size is. Are there 100 people in the population, 200, 150, 1,000 individuals? We typically do not have a list that gives us each and every element in the population. That tells us basically what the population size is. Another problem is that sometimes the population sizes are large. So let me change my example a little bit here. So this time I'm going to assume that I have a larger sample size. So I'm looking at a large university, and there are 25,000 students that study in this university. This is the population size. I want to understand these students. I want to understand, for example, what is the average age of students in this large population, or what the average height of students is, or what the average what the proportion of smokers in this large group of individuals is. There's some sort of a feature of this population, some variable that I'm interested in learning about. Now, 25,000 is a pretty large group of individuals. So if I were working on some sort of a problem alone, let's say I wanted to understand the average age of these 25,000 students, then in order to use all of this population data, in order to access all of this population data, I will have to physically approach each and every student and ask them for this information. Or alternatively, I would have to contact them, maybe using their email addresses, and ask them how old, each individual person, I will have to ask them how old they are. That is a lot of work. So assuming that I do not have access to the email information of all of the students in this university, I'll have to go and physically ask each individual person the same question: how old are you? And that is a lot of work. I will need help from maybe some graduate assistants, some other students. I will need to hire them so they can help me with this task. Because by the time I start with the first person and reach all the way up to the 25,000 person, I would have spent maybe weeks or months on data collection. And remember, in these kind of data collection efforts, we are not really interested in a single variable. Sometimes we are collecting information on dozens of variables, sometimes we're collecting information on hundreds of variables, and so on and so forth. And since I have other things to do, I teach courses, I have to work, I have to spend time with my family, there's only a limited amount of time that I can spend on data collection every day. So if I try to do this alone, it will take me a lot of time. We'll further assume that I don't even have the resources to hire some workers who can help me with this task. I don't have the money, and I want to complete this in a reasonable amount of time. I don't want to spend months or weeks on this kind of data collection. So in these kind of situations, when serving the entire population or observing the entire population, asking everybody in the entire population the same question is not feasible. Because of time constraints or money constraints or because of other reasons, then we do the next best thing. In these situations, the next best thing is to select a representative sample from the population. So instead of serving all 25,000 students in the university, I go to a place where students from all different departments and all different colleges congregate. So a student union, for example, or a central hall, or a library maybe, where students from all departments gather. And then I select a representative sample from this place. So instead of 25,000 students, I go to the student union or the library or maybe the cafeteria, and I select a sample of, say, 50 individuals. Now this is a manageable number, right? It is reasonable to collect data from 50 students. 25,000 students, I don't have the time, I don't have the money for that kind of data collection, but 50 students is a reasonable number. I can easily collect data from 50 students in a day or two. So the sample is a subset of the population, and when we do not have access to the entire population, we do the next best thing, and we select a representative sample from the population and then use that sample for analysis. So the basic idea is that I will describe the individuals in my sample. I learn basically whatever I can from the sample and then generalize that information back to the population. But we are kind of getting ahead of ourselves. What I've just described is called inferential statistics. This is one of the two main branches of statistics. The two main branches of statistics are descriptive statistics and inferential statistics. What I just described here is inferential statistics. Let me postpone a discussion of these two terms for a few minutes. Let's first figure out why we are learning about this population and sample, why this distinction is important. Now notice that we started talking about the population and sample after we talked about the different values of variables in our sample data, in our data set. I shouldn't call it sample data, because right now we have no idea whether the 5 individuals in our table, they represent a sample or a population. So these 5 individuals who provided us information on their age, height, and smoking status, they could be a part of the population. This could actually be the large group of individuals that we were originally interested in, or this could be a sample. You cannot tell whether you're working with population data or sample data by just looking at the table itself. The table has just a bunch of rows and a bunch of columns. So if this is population data, then we're really talking about a large group of individuals, or the primary group of individuals that we want to learn about. And if this is sample data, then we know that these 5 individuals represent a large group of individuals, or at least a group of individuals that's larger than 5. So from our point of view right now, since we are just interested in data, we are just interested in variables and observations, in other words, columns and rows in that data set, in that table, we don't have to worry about where the data comes from. It could come from the population, it could come from the sample. From our point of view, the table is going to look the same. The only difference is that if we have more individuals in the population, then we'll add a couple of additional rows, maybe a couple of additional observations will be added. But other than that, nothing is going to change, right? So let's say the 5 individuals that we obtained the data from, they are actually a part of a sample, and this sample comes from a population. So instead of the sample, if I actually had access to the entire population data, the number of rows in that in this table would be a little bit larger, depending on what the difference between sample size and population size is. So if my population size was 100, then there would be 100 rows in this table, right? We'll use some additional examples in a couple of minutes to further understand this relationship between observation and variable. We'll talk about different units of analysis. So I'll cover some additional examples in a few minutes. But first, let's discuss the difference between descriptive and inferential statistics that I mentioned a little bit earlier. So descriptive statistics and inferential statistics, these are two main branches of statistics. So let's step back a little bit and think about what we have done so far in this video. We talked about statistics. Statistics was defined as the science of data, and I asked you to think about a very specific format. I asked you to think about a table that consists of rows and columns. Each row in this format is called a variable, and each observation is represented by an individual row. So this column of variables and observations, I asked you to think about this as data. This is a flat data table, and this is what you should be thinking about whenever you see or hear the term data in this course. Now, in statistics, there are two basic types of procedures. So all the methods that we come across in statistics, they can be classified as either descriptive or inferential methods. What is the difference between the two? The difference is that in descriptive statistics, our aim is to describe data. We want to get to know our data. We want to understand the different types of variables that are applicable to our observations. Let me use a simple analogy here, which will make this concept a little bit easier to understand. Let's say I'm working in my office on a particular day, and during lunch hour, I walk out, I step outside because I'm feeling hungry. I want to go grab a lunch from a restaurant, or maybe go back home very quickly, eat some lunch, and then come back to my office. So I step out of my office around 12 o'clock during lunchtime, and while I'm gone, somebody stops to see me. So somebody stopped by and asked for me. So since I'm not there, the department secretary tells this person that Professor Chima is not here, please come back at another time. So the person leaves. When I come back to the office, the secretary tells me somebody came to see you. Now, naturally, I'm curious. I want to know who came to see me, who stopped by to see me. Now, since we are talking about a human being here, I'm going to ask questions about this human being. I'm going to ask questions that are related to the different features that human beings have. This will help me pinpoint the identity of this person. So I will ask the secretary questions like, what can you tell me about this person's age? Was this an old person or was this a young person? So in my mind, I work in a university. I'm thinking about, well, if this was a young person, it was probably a student. If it was an older person, maybe it was one of my fellow colleagues, another professor, maybe a staff member, and so on. So I'm trying to narrow down the list of individuals who might have stopped to see me. And then let's say the secretary answers this was an older individual. Now, I know many older individuals at my workplace who could have stopped to see me during the lunch hour. So I'm going to ask additional questions. Was this person a male or a female? What kind of clothes was this person wearing? Did this person have any glasses? Was wearing any spectacles? Did this person have a beard or other facial hair or something like that? So I'm essentially asking questions that are applicable to human beings. I'm thinking about different characteristics that a person has. A person has a weight, height, age. A person wears certain types of clothes. has or does not have facial hair, has a gender, has a male or a female. So I'm asking all these questions. I'm thinking about these different attributes so I can pinpoint the identity of this person. In statistics, we try to do the same thing. Our objective is to understand our data. Our objective is to understand our variables. So I would ask different questions that help me pinpoint the identity of those variables, help me understand my data. When you think about concepts like height and weight and age, you can relate to them because all of you are human beings. So when I ask somebody what your age is, they completely understand what I'm asking about. When I ask somebody what their height is, they understand what the height of a person is because they themselves have this concept called height. It is applicable to them. That person is maybe 5 feet 4 inches tall or 6 inches and 5 feet or 6 inches tall and so on. So they completely understand what this concept of height is or age is or weight is and so on. It's the same thing when I'm looking at a different group of individuals. So now let's change our example a little bit. So in my first example, I was thinking about a person who stopped by to see me, and I was asking different questions and that captured the different characteristics of this person. Right? So let's generalize that. Let's say I'm looking at a group of individuals, and this group of individuals has certain characteristics. Let's say we're looking at a group of students. So all of these students have a characteristic called academic major, right? So person number 1 is, for example, a marketing major. This is what this person is specializing in. Person number 2 is an economics major, a different major. Person number 3 is a physics major, and so on. So this is one feature that students have. Students are the unit of analysis in this example. The unit of analysis is an individual student, and each observation or each row in this table represents a student. Each column represents a feature of these students. I've already looked at a feature called academic major or just major, which is basically the main subject that these individuals are studying at university. But these students have other features. Another feature is, for example, that each student has something called an exam score. This is the measure of student performance. So let's say when we ask these 3 individuals what their latest exam score was, we get a variety of answers. And we'll assume that exam score is measured on a 0 to 100 scale as a percentage. So person number 1 tells us that this person had a score of 80% on their latest exam. Person number 2 scored 75%, and person number 3 had a score of 98%, and so on and so forth. So we have a different type of a variable that is applicable to these students, and that is exam score. So academic major and exam score are 2 features that students have. In this example, we are interested in these 2 features for the 3 students in our group. I'll assume that the group is actually representative of a sample. So these 3 individuals are part of a sample and not a population. Now notice what happens when my unit of analysis changes. So instead of a student, now let's say I'm interested in looking at a group of cars. So my unit of analysis is a car. And I'll keep the example simple again. We'll keep the data set small. This time I have 3 rows and 3 columns, and each row in this table represents an individual car. So car number 1 goes in row number 1, car number 2 is represented by row number 2, and so on and so forth. And each individual column represents a different feature of these cars. Now cars do not have academic majors. A car cannot specialize in marketing or economics. That does not apply to a group of cars. Car also does not have exam score. Academic major and exam score were features that were applicable to students. Cars have their own features. For example, each car has something called number of miles per gallon or fuel efficiency, or number of kilometers per gallon or per liter, whatever unit you want to use. That's the fuel efficiency, how much distance the car covers in a specific unit of fuel. So let's say we are measuring fuel efficiency in number of miles per gallon. This is the unit that is used in the United States and some other countries. And let's say the number of miles per gallon for car number 1 is 20 miles per gallon. And for car number 2, it's a little bit less at 18. Car number 3 is very fuel efficient, and it does 28 miles per gallon, and so on. So some hypothetical numbers here. I'm using miles per gallon as an example of an attribute because that is a feature That applies to cars. And in our example, this miles per gallon is a variable. This attribute is a variable because I see different values in this column. There are multiple values in this column. Remember, as long as any two values in a column are different from each other, that column represents a variable. What other features do cars have? Cars have a feature called make. Right? This is the type of car based on the car manufacturer or the company that made that car. So car number 1 is a Toyota, car number 2 is a Honda, and car number 3 is, let's say, a Ford. Again, I have different values in this column, so the make of a car or an automobile is also an example of a variable. Another example of a feature that cars have would be the size of the engine, or the number of doors, or the weight of the car, or the year of manufacture. So let's say car number 1 was manufactured in 2010. There's a 9-year-old car. Now is assuming that now is 2019. Car number 2 was manufactured in the year 2015, and car number 3 was manufactured in, say, 2019. So again, we have different values in this column. So this is another example of a variable. Now, the important thing to realize here is that when I was looking at a group of students, they had some attributes that were of interest to me: academic major, exam score, grade point average, quiz score, age, height, weight, email address, phone number, the location, the city where the student lives or where the student was born, number of parents, number of people living in the house, and so on. All of these are examples of features that students have. How far their house is from home, do they take the bus to school, or do they drive to school, to their campus, and so on. Similarly, a group of cars have features, but this is a completely different list. The features that are applicable to cars are completely different from the features that are applicable to human beings. Cars have features like color, make, model, number of miles per gallon, size of the engine, type of fuel, diesel, gasoline, and so on and so forth. These are the different features that are applicable to cars. A third example. Now I am looking at a group of buildings, and this group of buildings has completely different features. So in my sample, from right now in this discussion, I'll assume that I'm working with sample data, and I use lowercase n for sample size. So in this third example, my sample size is 4 because there are 4 rows in this table, and each row represents a building. So my unit of analysis now is a building. Building number 1 goes in row number 1, building number 2 is in row number 2, and then buildings 3 and 4 are represented by rows 3 and 4. So my unit of analysis has just changed. My unit of analysis is now an individual building. I'm looking at a group of buildings, and these buildings have completely different features. Unlike human beings, buildings have their specific features like number of floors, right? That's one feature that buildings have. Buildings do not have features like an academic major or exam score. Clearly, those attributes are not applicable to buildings. But each building has a number of floors or a number of stories. So let's say we're talking about 4 buildings, and building number 1 is a single story building, and building number 2 has 10 floors. It's a large office building. Building number 3 has 3 stories, and building number 4 has 2 stories. I see different numbers in this column, so this is an example of a variable. There are other features that buildings have. For example, the price of a building. Price is something that's not applicable to people. It is applicable to cars. So it's sometimes possible that you have the same variable that is applicable to different unit of analysis, right? I did not use price in my example when I was looking at the group of cars. I just looked at miles per gallon, make and year. But there could be another feature that records the price of each car. So buildings have a price. So let's say I'm measuring the price of buildings in dollars. Building number 1 is $30,000. That's the price, the going price of this building. It could be an estimate. Building number 2 has a price of $100,000. In fact, it should be probably more. I'm located in the US, and if you have a 10-story building in a large city, it would be pretty expensive. So let's make this $500,000. This is probably still a low estimate if you're living in a large a large city, but it really depends on your location, where you are located in that city, and what kind of a condition that building is in. So we'll assume that this building is $500,000. And then we have building number 3 that has a price of $200,000, maybe a very expensive home. And then we have building number 4, the last observation in this data set, that has a price of, let's say, $25,000. So there are 4 buildings, and we have their prices. So price is another example of a variable. It's a variable because in this column we have multiple values. We have multiple prices. As long as any 2 values in the column are different from each other, that column represents a variable. It's not a constant. So we have looked at 2 different features that buildings have: number of floors and price. And then somebody designed the building. So we have an architect, or the city in which the building is located. So let's say we have the city here as well. So building number 1 is located in city A, buildings 2 and 3 are located in city B, and building number 4 is located in, let's say, city C. So we have 3 different cities, and I'm just using hypothetical names here: city A, city B, and city C. And these buildings are located in different cities. So city is also an example of a variable because there are different values in this column. So we have looked at 3 different features that buildings have: number of floors, price, and city. The important thing here is that as our unit of analysis changes from a student to car to building, the group of variables that are applicable also changes. So for students, we have a certain certain types of variables that are applicable to those students, like academic major and exam score. For cars, we have a different group of variables that are applicable: miles per gallon, make, year, type of fuel, and so on and so forth. For buildings, we have a different set of attributes, or a different set of features that are applicable. So I'm going to go one step further, and this is where sometimes things get a little bit confusing for students. I'm going to, in principle, do the same thing that I've done earlier when I was looking at a group of students, or a group of cars, or a group of buildings. I'm going to do the exact same thing, with the difference that this time I will have a group of variables represented by rows. So my unit of analysis now is a variable, right? This is a little bit unusual because we always put variables in the previous examples in columns, right? So when I was looking at a group of students, my variables were academic major and exam score. When I was looking at a group of cars, my variables of interest were miles per gallon, make, and year. This time, I'm putting variables in rows. So I'm looking at a group of variables themselves. I want to understand those variables. Again, going back to my previous 3 examples. In my first example, I was interested in understanding a group of students. In order to understand those students, I had to look at the different features that those students had. In my second example, I was interested in understanding a group of cars. I was examining a group of cars. And in order to understand those cars, I had to look at the different features that those cars had. When I was looking at a group of buildings, I paid attention to the different characteristics that those buildings had. Now I'm interested in a group of buildings. I'm interested in a group of variables. I want to understand some variables that are of interest to me. And in order to understand those variables, I need to think about the different characteristics that these variables have. Variables do not have an academic major. Variables do not have a year of manufacture or a price, but variables have their own features. So let's talk about some of these features that variables had. What are those features or those characteristics that are now applicable to variables? So my unit of analysis is a variable. I'm going to put variable number 1 in row number 1. Variable number 2 goes in row number 2, and so on and so forth. Variable number 3 is represented by row number 3, and variable number 4 is actually my observation number 4. It goes in row number 4. So what are the different features that these variables have? If I wanted to understand some students, I need to think about the different features those students have. If I want to understand cars, I need to think about the different features that cars have. I want to understand buildings. What are the different features that buildings have? Now I want to understand variables, a group of variables. I need to think about the different features that variables have. Each variable has a feature called a center. There is another feature that is applicable to all variables. It's called variability. Other features of interest are skewness. I'll add another one here in the list. A fourth feature called kurtosis. So in principle, we're doing the same thing that we did earlier. The only difference is that these terms that I've just written here, these characteristics, these might sound a little bit alien to you right now. It's very easy for you to think about an academic major. If you have been to school, if you have been to a university, you understand what I mean when I say marketing major or economics major. It's very easy for you to understand what an exam score is if you have ever been a student and you have taken an exam. When I say somebody scored 80% on an exam, you know exactly what that means because you have some experience with that. When I say I'm looking at the make of a car, it could be Toyota or Honda or some other manufacturer, you can probably understand that because you either own a car or you're familiar with the car, you have seen a car, ridden a car, you can identify with that topic. When I was talking about a group of buildings and I said I was interested in the number of floors or the price of the building, you can understand that concept. When I talk about the number of floors, you're probably thinking about a building that has multiple floors. When I talk about the price of a building, you're thinking about the price in a very specific unit. I was thinking about price in dollars, but if you live in Europe, Western Europe especially, you would be thinking about price in euros. If you're living in Russia, you would be thinking about price in yuan. I'm sorry, not yuan, rubles. They use rubles in Russia. If you are in Saudi Arabia, you would be thinking about reals. If you are in Pakistan, you would be thinking about rupees and so on and so forth, right? So you would have some sort of a mental idea. You understand what this concept of a price is. You understand what the concept of an academic major is, or what the concept of a make or fuel efficiency for a car is. Now when you're looking at, you're doing the same thing with variables, but now you might be a little bit lost. What is the center of a variable? I cannot think of a variable. I cannot think of a picture. What is this thing called center, right? And this is completely understandable because these are terms that we do not use in day-to-day life. We don't typically talk about variability in a variable. We don't talk about terms like skewness and kurtosis. So it's difficult for most people to imagine what these concepts look like because they haven't actually they haven't read about these concepts or studied these concepts before. But the bottom line here is that just like in order to understand other units of measurement, I had to focus on the characteristics that were applicable to those units of measurement. Like, for example, different characteristics for buildings or cars or students. In order to understand a group of variables, I need to understand the different characteristics that those variables have. Each variable has a characteristic called a center, a characteristic called variability, and features like skewness and kurtosis. I will not be able to understand my variable unless I can understand those characteristics. Now, this was a very long description of one of the branches of statistics. Remember, this is what motivated our discussion. This entire example was to explain what descriptive statistics is. Descriptive statistics is where we are trying to understand our variables. And in order to understand those variables, we need to understand their different characteristics. So with descriptive statistics, we try to understand the center, variability, skewness, kurtosis, other types of features that our variables have. Different types of variables have different types of characteristics. They're made in different ways. So we need to get a handle on this. Without that, we'll never be able to understand what our variables represent, what our variables look like. We won't be able to build a mental picture of these variables. So center, variability, skewness, kurtosis, these are some of the things that we need to understand in order to describe our variables, in order to get to know our data, in order to get to know our variables. We also use some graphical tools, simple charts like the bar chart or the pie chart to do the same thing. But the essence is that in order to describe a variable, we need to understand what its characteristics are. We summarize those characteristics, and any tools, statistical tools, whether graphs or numerical methods that we use to do that, they fall under this category of descriptive statistics. The second branch of statistics, it has a different aim. It's called inferential statistics. Inferential statistics. The first one is descriptive statistics. The second branch is called inferential statistics, and its aim is very different. With inferential statistics, our primary aim is not to describe data, but to generalize information. You can also think of that as generalizability. So with inferential statistics, we are typically interested in a large group of individuals called a population. The large group of individuals represented by this large circle that we are interested in. It could be a large number of people that we are interested in. We want to understand something about these people. We are interested in a particular aspect or characteristic of these individuals that is of interest to us. So for example, we might be interested in the average age of these individuals, or the height or weight, or some other characteristic that these individuals have. Now, oftentimes we do not have access to the entire population because of the cost constraint or because of the time constraint. If we do have access to the entire population, then we don't need to select a sample. We can just describe the data in the population and we're done with it. But whenever we are forced to work with a sample, because there's no other alternative, we cannot look at all population data. Whenever we have to work with sample data, then the problem of generalizability needs to be addressed. And generalizability is essentially this problem. So I have 25,000 students in my sample, and these students have some sort of an average age. Let's represent that average age by Greek letter mu. So X represents the age of a person. The 25,000 students in our sample have each of one of these individuals has an age. And I want to calculate the average age of these 25,000 people. I'm going to call this average age mu. This is Greek letter mu, and this is the standard notation that is used for population mean. It's just an average. I'm getting a little bit ahead of myself. The arithmetic mean is a special kind of an average. Right now, think of average as a typical value that represents all other values of a variable. So I'm interested in this particular feature. I'm interested in the average age of all individual students in this population. Now, if I do not have access to all 25,000 students in the population, then I will have to do the next best thing. I'll have to select a representative sample, which in my example is 50. I will collect information on age from these 50 students, calculate the average age, which I'm going to denote X bar. That's the standard symbol for a statistic called the arithmetic mean in the sample. You can think of that as a typical value for age. So I calculate the average age of the 50 students. Now, my question is, I've calculated the average age of 50 students. This is a small subset of the population. And let's say this average age of these undergraduate students is 20 years. How can I be confident that this number 20 can be applied to the population? Based on this average age of 20 that I've calculated in the sample, is it reasonable for me to say that the population average is also 20 years? Or is it very different from 20 years? This is generalizability. When I take information from the sample and apply it to the population, I'm generalizing. I'm making a prediction. This is sometimes also called making a forecast. I'm drawing inferences. All of these mean the same thing. Drawing inferences or conclusions about the population, generalizing from the sample to the population, making predictions, making forecasts, different ways of saying the same thing essentially. What I'm basically saying here is I have calculated something from the sample. Can I apply it to the large group of individuals, the population? And if I can do that, how much confidence do I have in this generalizability? When we try to do this thing, whenever we go from the sample to the population, generalize information that way, then any methods that are used to do this, they fall under this category of inferential statistics. So I hope the difference between descriptive statistics and inferential statistics is clear to you by now. In descriptive statistics, we are trying to get to know our data. We are trying to understand features that our variables have, features like center, variability, skewness, and kurtosis. We're trying to get to know our data, trying to understand our data so that we can work with that data. With inferential statistics, our aim is a little bit different. We're not interested in describing data, but we are interested in generalizing data from a small subset of the population called a sample back to the population, back to that larger group of individuals that we're interested in. All right, I feel a little bit lost at this stage. Concepts, these are the kind of concepts, introductory concepts, where one concept leads to another, and it's very easy to get lost. So let's review what we have learned so far in this particular session. We talked about statistics. Oops, I deleted something by mistake. We talked about statistics, and I defined statistics as the science of data, right? I used a very simple definition of statistics. I call this the science of data. Now you should be able to appreciate why statistics is a science. Statistics is a science because when we generalize information from the sample to the population, we have to follow a certain set of steps, a certain set of rules. These are very inflexible rules. It doesn't matter which discipline you belong to. You could be in finance or accounting, a non-business discipline like physics or biology or economics or psychology. It doesn't matter which area you belong to. Whenever you generalize from the sample to the population, you have to follow a series of steps. It is in this respect that statistics is a science. If we have 50 different individuals, they're working with the same data, all of them will follow the same steps, right? They will. These steps are essentially you basically form some sort of a theory, which is formally called a hypothesis. You go into the field, collect data, and then based on that theory, based on that data, after you have applied some statistical methods to that data, you will either reject the original theory or you will not reject it, right? This is, in short, the scientific method. So for this reason, statistics is a science. Now you should be able to appreciate why I call this a key term when I first talked about this definition. The second key term here is data. Statistics has something to do with data, and you should be very comfortable with this term by now. I asked you to think about a very specific pattern, a grid-like pattern that consists of rows and columns. Whenever you see or hear the word data, this is called the flat data table, where each row is called an observation and each column is called a variable. So you should also be very comfortable with this concept of observation and with this concept of variable by now. An observation is basically your unit of analysis. Observations are elements or individuals that we are interested in examining. And variables are the different features that these observations have. So I used many different examples in my discussion today. When we were looking at a group of persons or a group of human beings, we were interested in different attributes that these human beings had: age, height, weight, smoking status, and so on and so forth. These are different attributes or different characteristics that people have. When we talked about a group of cars, those cars had completely different features: miles per gallon, make, model, type of fuel, year of manufacture, and so on. These were the different attributes that were applicable to cars. And then in another example, we looked at a group of buildings, and that group of buildings had a completely different set of features: number of floors, architect of the building, the person who designed the building, price of the building, city in which the building is located, age of the building, that's another attribute, number of safety features in the building, and so on and so forth. These were all the different features that buildings had. And then we applied the same concept to a group of variables. So in principle, it's not something new. The only difference is that now we're placing variables in rows, and we're interested in the different features that these variables have. And what are those different features? These features are center, variability, skewness, and kurtosis. And why are we really interested in these different features? So that we can understand our data, so we can describe our data, so we can use the methods and tools that are included in descriptive statistics in order to summarize our data, better understand our data. We also talked about the two branches of statistics. One of these is descriptive statistics, where your aim is to understand your data. Just like when you're trying to understand a person, you're going to ask different questions that relate to this person. So if I'm trying to understand a person, I'm trying to get to know a person that I've just met, I'll ask this person different questions. How old are you? Where were you born? What kind of language do you speak at home? What's your favorite food? Which university did you go to? Are you married? Do you have children? These are all the questions that make sense in this context because I'm trying to get to know a person. Right, so a person has a favorite food, or they have a favorite movie, or they drive a certain kind of car, or they have a certain income, or they're married or not married. These are different characteristics that people have. When I'm trying to understand my data, I need to understand the different characteristics that my data has. These are center, variability, skewness, and kurtosis, among others. With inferential statistics, the second branch of statistics, we are interested in generalizing information from a sample to the population. So this is obviously applicable in those situations where the complete sample data, the complete population data is not visible to us. If we had access to all population data, then there is no need for inferential statistics. We can just describe the population data using features like center variability and so on. Inferential statistics exist only when we're working with a sample. That's when we want to know if our sample estimates are good representations of their population counterparts or not. So if average percentage of students who pass the class in the sample is 50% or 60%, can I take these numbers and apply these numbers to the population with a high degree of confidence? Does this information generalize to the population? If the average age of students in my sample is 20 years, can I also say the same thing for the population, that the average age in the population is also 20 years? And if the answer to this question is yes, how confident can I be in my generalization? These are all, and this is what we try to answer. This is the main question we try to answer with inferential statistics. So depending on the methods or techniques that you're using in a particular context, these methods are either inferential or descriptive, or could be a combination of both. In most practical problems, we use a combination of descriptive and inferential methods. We describe the data first, and then we are also interested in generalization. All right, so this was our overview of some key terms. The takeaway and the main terms from this discussion are definition of statistics, what is meant by data, observation, variable, unit of analysis, how is a variable different from a constant, difference between sample and population, the two different branches of statistics, descriptive statistics and inferential statistics, and what are the different characteristics of a variable, center, variability, skewness, kurtosis. These are still probably difficult terms because these are new to you. These are probably something that you don't understand, but we'll talk about these features in more detail in future sessions.